My scenario is this. Only I put metasurface like this. It faces the source antenna like this. Source antenna doesn't have any inclination. 기울어지지 않았어요. And metasurface, the plane of the metasurface is exactly right perpendicular to the wall. So if this metasurface is wrongly designed, the energy doesn't go this direction outside of the room. This is a door opening. Wall, can you see that wall? Wall can be what? A screen that blocks the energy. So we took this very strict and stringent environment for our test. Here, wall. So if this is a simple metal surface, actually, especially, you can expect if your metasurface is well designed, you can detect the energy farther. Close to the area, you can detect the energy, but from where? Why? There's 3 angles, 0 degree, 12 degrees, 24 degrees. In the near field, there's a lot of noise, right? But in the far field, the target area is shown by the what? The energy. If we design or made the heating surface for the 0 degree angle of a reflection, like this, in the far field, noise is populated in the near field region, but in the far field region, I mean this. In the far field, it is quite prominent, but in the near field region, actually you can be, your experiment might be contaminated with the noise like this. So then it is hard to distinguish. This comes from where? It's a kind of environmental noise like that. To have a good angular distinction or discrimination, actually you should go many steps away from the door here. Another of my research assistants is holding the probe we developed. Get this millimeter wave measurement equipment at $16,728 US dollars. Very cheap. Anyway, we use our equipment to test. This is quite objectively acceptable to the industry. You can see the spectrum analyzer that shows this signal strength here. Anyway, my student is holding the probe where? Outside the door. The reason I take this example is if we test the reflector arrays or RIS in the open side or in the wide open area, like this. This is a simple metal surface, horn antenna, shooting the EM field here, incidence, and what? Reflection can be here, ray tube. So people might be deceived by that experiment. So my conclusions are, get this millimeter wave measurement equipment at USD like this can be one of them. But I mean, don't be fooled or deceived by so-called metamaterial people or RIS people. In continuity of what I was talking to you, regarding the role of the metasurface, as I told you before, this metasurface is designed to tilt the angle of reflection toward 41 degrees. As the flat surface, it is almost impossible in the past, but now it is possible by us to make a change in the flat surface to have a very special function like that. So the incoming wave is hitting the surface and the reflection occurs to the surface, but with the 41 degrees of angle inclination coming, still probe is waiting for the receiving energy or incoming reflected energy to detect. Here.
I have two versions of
as you
probe.
remember here, this
Stationary
position,
one, like this, with the tripod.
the
and
probe has
help.
not changed
You can find them under the name of
angular
TextWave
position.
5G.
It keeps the 41 degrees from the previous test, like this, right? But only difference we have made is the distance. The distance between the aperture of the probe to and the center of the metal surface, like this. So, well, 2 times the distance we used. Now we have this probe located at farther from the surface. The reason why I had to change the position of the probe farther from the metamaterial surfaces, if you see,
This is the best angular position which is targeted by the metal surface we designed, and we will move the angular position starting from 45 degrees to upper degree angle of reflection and lower angle of reflection.
Much
We will
noise,
compare them.
like side lobes. So sometimes it is hard to distinguish its feature at the 41 degrees or the strength at a lower degree like that. But if you move the position of the probe away to the farthest point, then the noise which was around it has been eliminated, and you can get the maximum strength at this position, at this angle. So we will going to check this. Let us confirm this by changing and checking the strength of the received power. Here we will read here the strength.
This spectrum analyzer is attached through the cable to the probe.
Some dBms.
You can see the green marker there that tells you the strength.
The signal strength has been lower than before. Why? At the same angular position, but the distance has increased. So it is no wonder we can see the weakening of the received power strength. But it's going to be the maximum at this same radial area. The distance is the same. This angle is going to give you the maximum signal strength. So please move this to a lower angle like this. How about this?
To a lower, one upper angle, a lower angle, but to this
direction.
Remember,
in the previous test, a little bit of lower angle from the 41 degrees, such as 20 degrees, the signal strength was not ignorable. Why? I told you the near zone area is polluted with a lot of
we've
noise.
changed the angle of observation from 45 degrees to 20 degrees, and we expect the decrease of the signal strength of the received power.
That's the farther point with the lower angle, but this is not the desirable angle. Desirable angle is 41 degrees here, about 20 degrees of angle. Let me check.
Let us check. Yeah.
That reads around minus 50 point something dBms. So you can see obviously the difference between the signal strength at the 41 degrees and the signal strength at the 20 degrees. So the noise has been removed. Why? We could do that by moving it further away from the surface of the material. Now we will change this probe to a higher degree of angle. Good. My research assistant has moved the angular position from 41 or 45 degrees toward around, say for example, that is around 60 degrees or 70 degrees, we are wondering what happens to this probe. Let us see the signal strength. That is minus 49 or minus 50 point something dBms. So the moving the probe from the
By watching
desired
the
to the upper
animation
angle,
on the
actually,
spot, it's hard to read the tiny
signal strength of the
numbers
computer
there.
power has
But
gone
I'm
down.
definitely telling
What we
you,
expected.
at the 45 degrees of observation, that was the best and highest in strength, around minus 40 something dBms. But other angles have, such as such as 20 degrees or 60 degrees, it will go down by 10 dBs like that, or more than 10 dBs. 그러면 지금 시간이 거의 다 됐지만 짧게 handheld 타입도 한번 볼 수 있을까?
예, 바로 드리겠습니다.
짧게 너가 스킵 해라.
Now I'm going to introduce a new probe, which is handheld. My research assistants are holding
For
this
you to
new
use
probe. Actually,
the
this
handheld
probe,
probe,
born to
you will need extra things such as the Steadicam fixer or holder. Then
the stationary
that might be
version.
much better for you to have just
handheld,
right answers.
version instead of being stationary. So stationary version was held by the tripod, but you can hold it with your hand. Now it is positioned at the angular position of 41 degrees. If you extend the line from the center of the metal surface to this is 41 or 45 degrees. So minus 41 dBms is read there.
Did you see a spike there?
This is hopefully the strongest point.
That means,
in the angular,
at that angular position, or in the azimuth plane, that has a certain value of strength.
더 좋아졌어요.
Yes, then a lower angle, such as 20 or a kind of extremely lower angle,
near field
just
region or Fresnel region,
7
that's
degrees or
why
something.
even at a lower degree of angle for the reflection, you can get not ignorable signal strength. But what happens to the change to a higher angle? 얼마?
지금 마이너스 43 정도.
Handheld probe to 80 degrees or 90 degrees.
It is quite compatible and have a consistent result for analysis.
Goes down.
I mean, the results, the value